So for this part, we're doing full-on word problems involving the central limit theorem. So here what we're going to do is we're going to start by reading the prompt, pulling out the key numbers. Suppose the mean number of apartments a person lives in by age 30 is 8 with a standard deviation of 2.2. Sample of 60 people, age 30 is taken. Within this prompt, there is one number that's a distractor, specifically 30. The fact that people are age 30 really doesn't impact the math at all. What I care about is the average number, the standard deviation, and how many people are being sampled. So the average is 8 apartments. In this case, mu equals 8. The standard deviation is 2.2, so sigma equals 2.2. Finally, it's a sample of 60 people, so n equals 60. Really, these are the three key things that I need to pull out of the prompt. What was the original average? What was the original standard deviation? And how many people are involved. When I look at part A here, part A is actually like what we did the class before. Where here, we're not concerned with the sample of 60. We're just saying, what's the case for one individual? So for this one, I set up my z-score as the 9 apartments that we're looking for as my x, minus the given mean of 8, divided by the original standard deviation of 2.2. Here we're using the original standard deviation because they asked about one person, not the mean of the sample. When I put this into my calculator, 9 minus 8 divided by 2.2 gives me a z-score of 0.45 repeating. Since I only want the first 2 decimals, I'm going to call it 0.45. Once I get that z-score, I need to go to my table. Within my table, I'm on the positive side. When I look up on the positive side, 0.45, it points me to a p-value of 0.6736. Because this was a less than question, I can stop right there, and that is the correct answer. So remember, that's for one individual person. When we now do the same calculation in part B, the only change is going to be, since it's asking about the mean of the sample, instead of using the original standard deviation of 2.2, we're going to divide by 2.2 over the root of 60 to make it applicable to a sample of size 60. So here, same z-score formula, same 9 minus 8 on top, the difference being on bottom, the 2.2 is now being divided by the root of 60. And again, the reason that we're doing that is because of these words, the probability that the mean of the sample, as opposed to these words, the probability of one person. So one person, we use the original formula before we learned the central limit theorem. When we're taking the mean of the sample, we use the version that divides by the root of n. If I now go into my calculator and I put in this version with the root of n, 2.2 divided by the root of 60, I now get a z-score of 3.52. When I look up that 3.52 in my table, it's actually so big that it doesn't even fit on my table. Whenever you get a z-score that's either too big or too small to be on the table, there's 2 choices you have. If it's too large a z-score, so big a positive number that it doesn't fit, your answer is going to be 0.9999 as far as what the p-value would be. If instead this had been negative 3.52, my answer would be 0.0001. So basically this table is good for all the values that are close to the middle, but as you get further and further into the extreme tails, we just have to assume it's either 0.9999 or 0.0001. So find the probability that the mean of the sample is less than 9. The probability equals 0.9999. The general idea here is, as we get more and more data and more people involved in the sample, things should bunch up closer to the mean. So if, for instance, we go back to my favorite example, finding the average height of a Manor student. If all we're doing is taking one person at random, we might get the tallest person on campus, we might get the shortest. But if we take 60 people at random, the chances of getting the 60 tallest people or the 60 shortest people are much, much lower than randomly just getting one of them. So essentially what happens here is because we have a larger sample size, things are packed more tightly, closer to the mean, so it becomes less likely that I get something further away from the mean. So getting something this far away from the mean, 3.52, means there's a 99.99% chance that we're less than 9 overall when we have that sample. Part C says find the probability the mean of the sample is more than 8.8. Starts out the same way as the one we did before. Trade in 8.8 where we used to have 9. Still have the mean of 8 being subtracted. Still dividing by sigma sub x bar, which is 2.2 over the root of 60. When I put this into my calculator, I get a z-score of 2.82. I then go to my chart to look up the associated p-value. When I go to 2.82, I get 0.9976. If this had been a less than question, I would stop right there. Because it says more than 8.8, I need to do 1 minus table value. 1 minus 0.9976 gives me 0.0024. The last question in this section is definitely the hardest one on the paper. It's something that's generally pretty confusing, but I'm hopefully going to be able to walk you through it with a couple graphs. Basically, find the probability the sample mean differs from the population mean by more than 0.5. Graphically looks like this. We have the original that's centered at a mean of 8. If I go 0.5 in this direction and 0.5 in this direction, that would give me two new numbers. 0.5 up would give me 8.5, 0.5 down would give me 7.5. So basically, if this had said differs from the population mean by less than 0.5, we'd be doing a between question using these two values and shade the area in between. Since it says by more than 0.5, we're actually shading the tails here. So the same way that we wanted to find outside of things by doing 1 minus the between answer, here we're going to find what the distance is between them and then do 1 minus that to find what the tail area is. So here's what that looks like. I set up a z-score for each number. First one's going to be 7.5 minus 8 over 2.2 divided by the root of 60. Second one's going to be 8.5 minus 8 divided by 2.2 over the root of 60. I'm going to put these into my calculator. Here I get a value of negative 1.76. Here I get a value of positive 1.76. It must be the case that if we move the same distance to the right and left, we have to get the exact same z-score, just one time negative and one time positive. If I look up the associated p-values here, the p-value for negative 1.76 is 0.0392. The p-value for 1.76 is 0.9608. So if I want to find the between area here, I'm going to take 0.9608 minus 0.0392. When I do that in my calculator, 0.9608 minus 0.0392 gives me 0.9216. So that 0.9216 is this unshaded area in the middle. If I want to find the shaded area in the tails, I do 1 minus that 0.9216 to get to the correct final answer, which is 0.0784. The other way I could have gotten there, I could have seen, well, since this is a symmetric table, this shaded area must equal this shaded area. So if all I do is look at the left side and find what's to the left of that, if I double that answer, that'll get me to the same place. So my left-sided value was 0.0392. If I just do 2 times that 0.0392, That would also get me to 0.0784. Both are valid ways of looking at it, but in general, it's going to be quicker. If you see that it's something that asks differs by more than a certain amount, if you just find the left-sided value, find its less than amount, and double that answer. That's going to be the quicker way to do these problems.